I hope you all had a very good lunch. And we kind of stopped talking in geometry representation for topology optimization. And I wanted to tell you about solid isotropic material with penalization approach. And here it works in the following way. So we define a design variable. By the way, was anyone able to find the slides online now? Still no. Okay, but the other slides are available, or? Okay. Okay. Well, thank you for pointing that out. Then I will double check. Oops. No, I ruined it. Okay, I need to start over. So we define a design variable xi. On an element basis. And in particular, this xi will describe the material content inside the element. Xi describes the material content of this element. Meaning that if xi is equal to 1, this element is full of material. If xi is equal to 0, the element is empty. And we view xi as an artificial density. So meaning that xi is the ratio between the density in this element and some maximum density that is associated with the full material, so with this isotropic material. And then based on this xi, the stiffness of the element is adjusted. Xi adjusts element stiffness. In the sense that the Young's modulus of this element is then computed as xi to the power of p times the Young's modulus of the full material. And p is somehow larger than 1. And this power law formulation, this punishes intermediate values. So this is why we need it, because otherwise we would have this homogeneous field, and all of the intermediate values, they're basically useless to us because we need to decide somehow, is this material or not? So we don't want the intermediate values. So this power law formulation helps us to punish intermediate values. But of course, again, there's the difficulty, how do I choose the p? If p is too small, then I have too many of the intermediate values still. If p is too large, then I'm starting to restrict the optimization space a lot. and I might not find the optimum that I would want. So there's also a judgment call here, basically. Okay, so this is the one option that we have these continuous variables. There's several kinds of continuous variables, but SIMP is the most commonly used approach. And then there's the choice of discrete design variables that usually occur in the context of finite elements. So based on various criteria, often stress-based criteria, we add or remove elements from the initial finite element mesh in the sense that we activate or deactivate them. So the position of the elements does not change. The finite element mesh always stays the same, but we can remove some of them in the sense that they no longer contribute to the stiffness matrix. And the first example of such an approach was evolutionary structural optimization. So here evolutionary refers, show all points. So evolutionary refers to the fact that the elements are successively added or removed in the sense of activated or deactivated. The finite element mesh remains intact during the optimization, meaning the number and positions of elements does not change. However, only the active elements will contribute to the global stiffness matrix. So here the elements themselves are the design variables. So our xi's are either 0 or 1, and there's nothing in between. The problem with ESO is that once an element is gone, you can never get it back. And of course, optimization takes different paths, and sometimes you would want it back because even if in the initial configuration there was low stress at this position, once the geometry changes, maybe this position now has high stress, but you cannot put the element back. And this is what is happening then in bidirectional evolutionary structural optimization, which allows to also reactivate elements. An example is shown here. So first, we actually have many steps of element activation here. And then at later stages, elements are also removed again. So from something that originally looked just like a line, you can get to this V shape. So this is the idea. There's a number of very typical difficulties in topology optimization. So we have these discrete values. So the problem is generally ill-posed. And this becomes particularly noticeable in grid dependence of the result. If you use a different mesh, you will get a different result, most likely. So you need some kind of regularization. So for example, SIMP is already a regularization in itself. If you don't use that, you need other ways of regularizing. And then even if you do some regularization, you will have two more problems. So emergence of microstructures and these checkerboard patterns. And this can be eliminated if the solution set is reduced. And this can be achieved, for example, by limiting the total volume or limiting gradients or maybe some filtering. And I will show you some impressions of checkerboard patterns and also how to resolve them. And the goal is then, of course, that the basic structure of the geometry no longer changes with mesh refinement. Then you know that you're on a good track towards an actual optimum. So here, first of all, you can admire my translation error. So Beispiel means example in German. So example for mesh dependence, whatever my brain was doing there. And so here we have a coarser grid and a finer grid, and we see that the structure actually still changes on the finer grid. So this would be one example. And then one measure against such effects is the perimeter control. So all three examples here, all three topologies, have the same proportion of material in the total volume. So the same volume fraction, but the total perimeter increases from left to right. So if we then introduce the total perimeter as an additional constraint, then we can prevent these small isolated structures, and we come to more global structures. Of course, like all of these parameters, the exact value of the constraint must be determined by a trial and error. So the same problem as always. Often one sees these checkerboard patterns. They're numerical artifact and not an actual solution of the optimization problem. They can be avoided, for example, with a more precise evaluation of the stiffness matrix using higher order finite elements or the previously mentioned regularization techniques. Okay, that brings us away from the parameterization. If you don't have questions right now, yes, please.
I can do something because in one slide I understood that to fix the checkerboard pattern you would reduce the solution set. But at some other point I think I understood that you could solve it by using higher order elements. But in that case the solution set becomes bigger. So maybe I mixed things up.
Yeah, so the question was about the checkerboard pattern. That on one slide it was said one should reduce the solution set in order to avoid checkerboard patterns, and now just recently I said that if you evaluate more precisely, then you can also reduce this effect. So I think it's a combination of both, basically. If you evaluate very accurately, you can afford a bigger solution set. If you're very coarse, then you need some kind of restriction in order to prevent these patterns. So now we move towards the objective function, and also this will be a chance to show some nice topology optimization videos. So this is our, let me go through all over this. Okay, this is our minimization problem for the topology optimization. So we want to find the optimal shape within an admissible set of our, with respect to our objective function J. And now here it's very important that we need to add some kind of constraint for the topology optimization. Because think about if you just want to, I have a design space, and I want to minimize the compliance. So I maximize the stiffness. The highest stiffness will definitely be obtained if I put material everywhere. So, but I don't want that because I want it to be light somehow. So I need this additional constraint on the volume saying that there's a maximum amount of material that the optimizer can use. It needs to decide how to distribute. If I can also switch it around. So this would be the compliance as the objective. I can also use the volume as the objective function, and I can try to minimize the volume. At that point, I have to put a constraint on the stiffness, because otherwise, you minimize the volume, everything is gone. Perfect. Yeah, so you always have these two components that have to interact. As objective function, you can also use maximal displacement. For example, that could be easier to compute if you have a beam and you have a force. I mean, this classic topology optimization problem, you have a force at the end of the beam. Then to compute the deflection there is very convenient. You can look at maximal stresses. You can also look at heat conduction, for example, like the thermal load capacity, the maximal temperature. So all of these things are possible. Let's go through how one actually computes this. So the compliance is for sure the most common objective function. Minimizing compliance means maximizing stiffness. We already said that before. And the formulation is as follows. So here is the standard mechanical potato. F are volume forces. Here T are surface forces. U is displacement. So if we want to, in this setting, compute the compliance, then what contributes are the volume forces and the displacements that are caused by the volume forces that are integrated over the entire domain. And we have the traction with the corresponding displacement on this Neumann boundary. So this is how we compute the compliance. How to compute the volume, I guess, is clear to everyone. Then let me go through here. So the maximal displacement is another form of stiffness maximization. I will try to fix that before the slides are online for you. So we look at the maximum of the displacement. And now this can be a bit dangerous for the optimization because the position of the maximal displacement will likely change during the optimization. So then we can have jumps in our objective function. Also, we cannot compute the derivative of this function. So this is not very convenient for us. Instead, one could use this formulation in the p-norm that sort of translates this maximum into similar to before a continuous formulation like we had with the sim sort of. So we take u to some power of p, we integrate over the domain, and then we take the appropriate root. And the same thing can be done if we look at maximal stresses. Also, maximal stresses can be something that one would want to avoid. Again, you don't really want to use the maximum function, but you use this formulation here in order to make it smooth. And then finally, also with the thermal load, or the heat temperature behavior. So thermal load capacity, we want to minimize the global temperature. So we have some heat source F and the corresponding temperature. So basically like the compliance that we had before, or we can look at maximal temperature, again, probably not in the formulation using the maximum function. Okay, as an example. So we have this beam, it's fixed on the left. We have a point load on the right bottom corner with the unitless value of 1. We have 300 by 100 finite elements. And now we investigate two scenarios. First, we minimize the compliance and we apply a volume constraint of 0.5. And then in the second scenario, we minimize the volume and we put a constraint on the maximal compliance. And just to look at the different effects. So here we see compliance as objective function, volume as objective function, and then we have the material distribution. So this is it was computed with the sim as a geometry representation, and this is the resulting material distribution. The compliance, or the minimal value of the compliance that was obtained, was 198.145, and the volume constraint was 0.5, and this constraint is kept here. This is those are the iterations of the optimization, and then instead, if one minimizes the volume, you see the overall structure is sort of similar, but here, for example, you get a different pattern as compared to here. In terms of value, but in terms of value, it's very similar. So this was the compliance that was given as the constraint, and this is the volume, which is really not much less than the 0.5 that was actually reached, but the shape is a bit different. The second test case, now optimizing with respect to maximal displacement. So now we have a line load. Again, the same finite element mesh. Scenario 1, we minimize compliance and apply volume constraints, so like before. Scenario 2, we minimize the maximal displacement and apply a volume. Oh, a question, yes.
Yes, how do you determine the maximal, the value of the constraint for the compliance? Did you base yourself on the result from the other?
So in this case, it was based on the result from the other computation. Oh, sorry, I forgot to repeat. So the question was how we determined the maximum value for the compliance. So again, in this case, because of the previous optimization, also because we wanted to compare the results, but in general, you would get that from some design constraints that you have, like then we're talking again about safety of your component and how does it need to behave. But here it's purely academic, just for seeing the difference. Okay, so now if we minimize the compliance, in this case, we obtain this result. Here we see the displacement field. And the corresponding values are as follows. So 29.215 for the compliance and 77.343 for the maximal displacement. Now, if instead we minimize the maximal displacement with P is equal to 32 in this case, then again, the result is sort of similar, but there are visible differences. And then this would be the displacement field, and those are the values. Then as a third test case, now we're looking at maximal stresses. So we have this L shape fixed at the top. There's a point load at this top right corner, which is distributed across 8 nodes. We minimize compliance under a volume constraint or minimize maximal stress under the same volume constraint. And here, if we look at the original optimization, that minimizes the compliance, we see that we have the stress peak here. So this is probably not a very good solution. Instead, if then one minimizes with respect to the stress, then this is much smoother in terms of shape. But of course, then the compliance is also higher. And then finally, the heat conduction, just because the shapes are so pretty. But let me say something. So we have this plate with boundary conditions. We have a fixed temperature here on the top in the middle. And we have a volume restriction of 0.25 and a homogeneous heat source throughout the entire plate. So you see, I said it's pretty. This is the material distribution for minimizing with respect to thermal load capacity. And then the temperature distribution within the plate. One can no longer say plate, I guess, within this structure. And then instead, if one minimizes the maximal temperature, I mean, here, then it gets very hard to distinguish. I mean, here's some smaller branches, but overall, it's really quite similar. So we sum up our learning aims. In geometry representation for the shape optimization, we spoke about the parameter base. So those were the splines, for example, and the parameter tree. So we shift every node in the computational mesh. In topology optimization, we can choose a continuous or a discrete representation. And then in terms of objective functions, we looked at compliance, volume, maximal displacement, maximal stress. It was important that we have this additional constraint, now an inequality constraint on either the volume or the stiffness. Yes.
Final shape. manufacturing now producing every shape is possible. But if it isn't, how it can be considered, for example, in object definition or even if it's possible or not. And the second question is about the software which there's are used here for this different let's say example. And also what software can be used in industry. For example, are there any built-in software in ANSYS, Abacus, and it's able to do topology optimization? Or it's just
Yeah, okay. Well, thank you very much. I will repeat, there were two questions. I will repeat the first question. So about whether it's possible to include constraints on the manufacturability of components. So let me first answer for shape optimization. If we actually have a parameter-based representation, then yes. I showed you the extrusion die, for example. We have the slope, which is a very clear feature. And in fact, we did, because this is usually manufactured using wire erosion. So you have some limit on the slope that you can easily impose. Now in topology optimization, now I'm not, beyond these academic examples, I'm not an expert on topology optimization. So I would like to answer that I'm not aware of how you would do that, but maybe someone in the audience. Oh, I see someone nodding. Okay, please go ahead. Let me give you a microphone, sorry.
Sorry, there are possibilities for topology optimization, sometimes related to AM, to additive manufacturing, and there are some works on this that they actually implemented the constraints such as overhanging, limiting overhanging to build the automatically supported the structure.
Do you know how?
I know, but we can discuss it later.
Anyone else that wanted to comment? And the second question was about software. So what we used here was a MATLAB code that was available open source. I would need to look up the name. I don't know by heart. For sure, commercial software like, so I'm aware of HyperWorks, for example, that has a topology optimization module, but I'm sure that also others offer it. Usually it goes under the name of generative design, I would say. Also, yeah. Yeah, I think everything basically, yeah.
Yeah.
Yeah. So I guess they usually call it generative design, and then one doesn't know what's going on at all. I find it very hard to understand what is happening. So we have this one lecture on numerical design, which covers shape optimization, but also topology optimization, and then there's a practical exercise with HyperWorks. But we found it very hard to connect the exercise and the lecture, because we teach all of these amazing methods, and then it's hard to pinpoint it to certain elements in this commercial software.
How we see the works with generative AI.
Yeah. Yeah. All right. That brings us to the final session. So my colleagues that come after me during the week, they told me I need to say something about neural networks, and I need to introduce variational autoencoders. So I will do that. Probably most of you already had some contact with neural networks, so it's not really new for you. So I was thinking, what should I do? And then I decided what the heck, it's fun because my colleague, she showed me, this was, she just, last year she had a baby and someone gave her a book that was called Neural Networks for Babies. I thought it's so cool, I wanted to show you because it's really neat. So this is a neuron, which will send messages through your body. And if you give this neuron an input and an output, then it can help to learn. So we replicate this neuron. We also have an input and an output, or it can have many. So this is how it works for the neuron. And now the question that we're trying to answer is there a red animal in this picture? So we divide the picture into 4 sub areas. And then for each sub area, we look, is there red or not? So here there's only blue, but here we see some red, here we see some red, here we see some red. So all of this goes into the neuron because we can have several inputs. So it sees 3 red, 1 blue, so it decides red, and then it can send out this message. It can propagate this information, red, to other neurons. Or we can try to see how many arms does this animal have. So again, we subdivide. For each section we count, then the neuron could add up, and it can send this message of 8 into the world. So where does it send it exactly? It sends it to other neurons because those are connected to a network. So then we have so-called input neurons that each see a part of the picture, and they give some information of this particular part that they see to other neurons. And then they process the information, and output neurons then give an answer about the picture and the way that they process, for example. So both of these hidden neurons are connected to all input neurons. This one makes decisions about the number of arms. This one makes decisions about colors somehow. How does it know? Well, we give it training data. We say this is green with 7, this is blue with 8 arms. And then if it gets a new picture, it can decide what kind of picture it is. So that was neural networks for babies. I just thought it was really cute. I wanted to show you. But what is happening exactly? So we look at an example with 1 neuron. So now based on this book here, no longer on the baby book. So what if we want to kind of convert kilometers into miles? Then we have some input, which would be the kilometers, we have an output, which would be miles, and we perform some kind of computation in there. So for now, we assume that we do not know the conversion formula, but we make the assumption that the relationship is linear. So something like miles is equal to kilometers times a constant. And then we get some training data, so some value pairs. So the first truth example is that 0 kilometers is 0 miles, and the second one is 100 kilometers is 62.137 miles. And now we refrain from directly computing the constant. We want to use this example, and we try an iterative scheme. So how about 0.5 for the constant? So the input would be 100, which is one of our truth examples. Output would be 50. Now we can compare to the correct value that we know from our table, and we can compute the error, which is currently 12.137. So we give this information back, and we know we need to increase our value for the constant. So we know the output has to take on a higher value, so constant needs to be higher. How about 0.6 then? So then input 100, output is 60, correct value the same as before. So we compute the error. It's now 2.137, so we improved, but it's still too high, so we increase again. So how about 0.7? Then output is 70. Correct value has not changed. So now we have an error of minus 7.863. So what happened is now for sure we went too far, because now our error is higher than it was before, just in an opposite direction. So what we should learn is that when the error becomes smaller, also the modifications should become smaller. So maybe we should have tried something like 0.61 instead of 0.7. So that's the first thing that we learn here. So what we saw here is a predictor. So we convert one number into another. But exactly the same structure can also be used for classification. So we have so with this, we're trying to mimic the behavior of a neuron. So we have some kind of processing here. Before we said we have a linear relationship. So it would be y is equal to ax plus b, something like that. But then if we look at the brain, then we see that neurons only fire the input signal surpasses a certain threshold. Otherwise, they don't do anything, and this will suppress noise. So if you think back with the neural networks for babies, and then if the whole portion of the picture is basically blue and there's a tiny little bit of red, it should probably not say that there's red. So instead of using this function here inside our neuron, we could use something like a step function, saying that after a certain threshold is surpassed, then the neuron starts to give an output. Otherwise, it does not react to the input. The step function is not very useful because it's not continuously differentiable. So instead of using the step function, for example, one can use the sigmoid function, which looks like this. And this is how it's computed, but there's many other functions. But you want to replicate this behavior, you have a certain threshold after which the neuron starts to react to something. So you have this artificial neuron, you have several inputs, you sum up the input signals, then you apply your sigmoid function or whatever other function, this is called an activation function, to this, and then through this you compute the output, y. Then you put them together in a network. So you have layers, a layer structure, you have your inputs, you have your outputs, and you have these connections between your neurons. And now which part of the structure is now responsible for learning? So we have the sum of the inputs that could be modified somehow. We have the activation function, and we have this connection between the neurons. And in fact, in the actual learning process, what will happen is that you adjust the weights of these connections between the neurons. So you have the process inside each neuron with your activation function and your inputs. The inputs that are coming in, they're weighted according to where they come from. And then the learning process happens by adjusting these weights. And the thing is that biological brains somehow can perform very sophisticated tasks, even though they have less memory than computers and they cannot perform operations as quickly. But somehow they manage. And in fact, also they're very robust to imperfect and damaged signals. And this is why they did serve as an inspiration for artificial neural networks to try to learn. So we said before that the error is kind of the driving force to how we adjust what happens inside the neuron. We also said that the size of the errors sort of tells us how much we should adjust. And if the error becomes smaller, also our adaptations should become smaller. So how can we translate this to a network? So we have some kind of output error that we can compute based on the training data that we have. And now, how do we split up this output layer to these two neurons in this output errors, or to these two neurons in the previous layer? Should we give each one half of the error, or maybe adjust according to the weights? And in fact, it makes sense to really adjust according to the weights. So here we have a weight of 3, here we have a weight of 1 currently. So here we would give 1/4 of the error, and here we would give 3/4 of the error in order to get an information on how to adjust this weight. So as I said, the error is divided proportionally among the nodes with respect to the weights. So the share of error 1 for updating W11 is this ratio, so W11 divided by W11 plus W21. And this, yeah, so then we would compute it like this if we go through several layers. So this is our output error. This goes back to this hidden layer. We can compute an error at the hidden layer through this relation with the weights. And then we can go through the whole network like this. And so here's an example. If the error is 0.8, we can divide it according to the weights. So then for this node here, we would get an error of 0.42. And yeah, this whole procedure is called error backpropagation. And this is how we can adjust the weights through several layers. So the neural network will learn by refining or updating the connection weights, and this is controlled by the error, which is somehow the difference between the correct answer given by the training data and the actual output. Yeah, the error at the output nodes is then simply the difference between the desired output and the actual output. The error assigned to the internal nodes is not that obvious, but then is split according to the connection weights in this error backpropagation process. In fact, this whole thing can be formulated as an optimization problem. Again, so for this purpose, we need an error function, cost function, or in our previous terminology, an objective function. For example, one can use the sum of squares of the errors, because we usually have several output nodes, so it's not only one value, but we need to average this somehow. So yeah, the sum of the squares of the errors can be useful.
Está tomando todo, se volvió loco.
Because it avoids that positive and negative values cancel each other out, so that's why the square. And also it assures differentiability as opposed to the maximum function, for example.
Otto, dile, hola papá, estoy aburrido.
So we have this null error at the output, which is then the truth minus the computed output. And for each, so then our objective function is this. We have the sum over all of the output nodes of the square of the error. And then we want to compute the gradient with respect to the weights. And this is, then we can use the steepest descent, for example, to move towards the optimal distribution of the weights. So this is our error function, but we compute the derivative with respect to all of the weights. And now this expression can be simplified, and this is what we will do on the next couple of slides. So the first thing that we realize is that for each output node, for each node in general, the output depends only on the connections that lead directly to this node. That means that the output at node K depends only on the weights WJK and not on the other weights. So the sum can be removed from this expression. So we go from this expression here with the sum to the expression without this. That's the first simplification that we can make. Now, I took what we had at the bottom here and I put it here. This was our previous step where we were able to remove the sum. Now, the next thing that we know is that the training data, TK, does not depend on the weights. So this can be factored out. So then we obtain this expression. Now I take this again, put it to the top right. This is where we were at. So the output of node K is calculated by applying the sigmoid function to the weighted sum of the incoming signals. So now here for the output, we plug in the sigmoid function and the incoming weights. We put this to the top right corner. Then we insert the derivative of the sigmoid function, which is defined as such. So we insert this here into the expression. Now, I wanted to put it here, but it didn't fit anymore. But the relevant part was this last expression here, which is again OJ. So this is the final expression for the derivative of the error function with respect to the weights. And this is then now we have the gradient, and now we can optimize the weights. Yeah. So key idea, the error of a neural network is a function of the internal weights. Improving a neural network means reducing this error by changing the weights, and the choice of weights is iterative, for example, using a gradient method. All right, now we come to a specific type of neural network. Yes. No, please. That's why we're here. Please ask questions.
Training is it as data to keep function bit of data. Data.
Yeah.
You just see that you create keeping a function.
Yes, so always it is a concept of fitting the function. Yes, so the idea is to approximate some function. Okay, so we start with a neural network that is used for image reconstruction, and this is the so-called autoencoder. It is a standard neural network, just like we saw before. However, it has a specific structure. So here we have the input nodes, we have the output nodes, and here we have the hidden layers. And you see that it has a shape like a tilted hourglass. So here in the middle, the hidden layer is much narrower than in other places. And now, the way that we train this network is that we give it a picture and we train it to reconstruct exactly the same picture again. So that doesn't seem to make much sense because we already have the picture. But if we look at this network more closely, then we have this so-called encoder part. We have a so-called bottleneck or latent vector, and we have a so-called decoder. Now, if we train with the pictures, then at some point automatically we will get a low-dimensional representation of our picture in this latent vector. So after training, just based on the latent vector together with the decoder, we can reconstruct pictures or images that can be sent to someone else just using this low-dimensional representation, which is a representation that was automatically learned. So this is unsupervised learning because we already, I mean, input and output is very clear. There's no reason to put labels on a bunch of training data or something like that. I mean, this is very clear what should be done. So this can be used for reconstruction or for denoising of images. So I want to show you these examples of neural inpainting where you have an image and something is missing here. And such neural networks actually manage to reconstruct these images very convincingly, I would say, even though a big chunk is missing. The other application is the denoising. So those were the original images with which it was trained. And this is then the noisy input that is given, and the autoencoder is then able from this to reconstruct the number that was in there very nicely. So this works very well. However, they cannot be used to generate new images. So if you have a bunch of images of rhinos and cats and dogs and I don't know, if and you take the latent vector that produces the rhino, then it will give you the rhino. But if you take something that is in between a rhino and a cat, you will not get some merging of a rhino cat, but you will just get something very random. So that's the problem with the autoencoder. Why it is not useful in, well, generating new content. And if we think about shape optimization, then we don't want to reproduce existing things, but we want something new. So then autoencoders are not very useful. So this summarizes again what I just said. Now think back to the shape representation. So we had this parameter-based, parameter-free, and in principle, what we're trying to do is that we have some high-fidelity geometry representation of a complex shape, and we try to squeeze this into few parameters. So this is very similar to this image reconstruction or image compression. So we want to find the key attributes, and we want to have a low-dimensional representation that gives us these key attributes. So that brought us to variational autoencoders. And I have this example video of what a variational autoencoder can do. So here you see a photo of a person, and here you see different attributes like male, age, skin tone, hairline. And then actually you can adjust these features and you can actually generate new images. So if one could do the same thing for shape optimization or form finding, that will be very nice. So what is so different about the variational autoencoder in contrast to the autoencoder? In principle, the structure is very similar. We have the input nodes, we have an encoder part, we have a decoder part, we have these latent variables or this latent vector, but this is not standard node in the network, but instead here we sample from distributions. So here we have probability distributions defined over their mean and their variance, and then we sample from these distributions, and this is what gives us the continuity. The question is then, what should the loss function maybe look like if we have this distribution? And how can I do error backpropagation through a probability distribution? So these are things that are then different for the variational autoencoder, but in principle, it works in the same way. So what we did in terms of shape optimization is that we have training shapes here. So those are also from manufacturing, in fact, also from extrusion. In the very beginning, I showed you these extruder screws, and sometimes there's so, yes.
Is there a data set for training shapes? An openly available data set?
So the question is whether there's an openly available data set for shapes, and yes, there is. So for shapes, there's several databases. They're usually not very engineering focused, so get a lot of chairs, rabbits, things like that. There's also, I guess, in the airplane sector, you can find quite a bit. So there are databases available for shapes. Yeah, so here we did not use one of these databases. We used our own shapes connected to extrusion. So those are mixing elements that are distributed on extruder screws. And we took some existing shapes and we trained the variation autoencoder to reconstruct these shapes. And in fact, after training in the operational usage, you can then morph between these shapes. So that did work very well. Yes.
How did you find the shape? Points from
Yes, very good question. The question is how we define the shape sign distance function. So here, of course, we have a very high variability. The shapes can be reasonably complex. The problem still, this latent space, one does not really have control. At least if you do it in the standard way, you don't really have control over what happens in the latent vector. So it could be good, could not be good. Also, for now, this is not CAD compatible because of the sign distance function. But I do think, so now Matthias is not here right now, but I think that last week he told me that they have a variational autoencoder with splines. So hopefully he will tell us this week that it also works with splines. If we look at the approximation quality, so this is the ground truth. Those were the shapes that we trained with. If the latent vector is 8-dimensional, then this is the reconstruction. You see that there's still some differences here, for example, with this half sphere, and the cap is basically cut off. But with the 16, what just turned itself off? It got really quiet somehow. Oh, yeah. It's like there's no AC in here. It's very hot. So, but with 16 latent codes, it's already quite nice. And I mean, 16 parameters, if you compare to a spline, I think it's quite reasonable for such shapes. Please, yes, you have a question.
Distance function is the property of continuous.
In our case, yes. Yeah. Sorry, yes. The reason for using the sign distance function was the smoothness or the continuity. Yes, please.
Did you find some kind of interpretability of the latent parameters?
No, not really. I know that there's some papers on hierarchical autoencoders where you do have certain features that are reflected in certain parts of the latent vector. So this we've not tried, but I know that in principle in computer science, this question is answered. Yeah, and this is the visualization of the latent space using t-SNE, which is a projection method that projects a higher dimensional space to a 2-dimensional space. And the property of t-SNE is that points that are close to each other in some sense in the high dimensional space are also close to each other in this 2-dimensional space. And here we see that, first of all, certain shapes are clustered in certain areas. So this is a desirable property. And, and we see the clustering. Never mind. All right. So our very brief introduction to neural networks. So they're capable of approximating even highly nonlinear relations inherent in the data. And we talked about variational autoencoders in the context of learning shape parameterizations. Okay, that 3. We're supposed to go on until 3:30. Okay, so then that gives us half an hour for designing your own spline. So I asked you to try to download the SplinePy module. If you've not done so, here's the installation guideline again. Excellent idea. Now that we don't need I think you can open it even more because we don't need the screen necessarily. And then here, I also sent it in the email. There's a Jupyter notebook that should guide you through some functionalities of the software. So you can generate Bézier splines, B-splines, NURBS, everything that we talked about. You can plot the basis functions, and you can try to design your own personal geometry that you need for your own application. Short disclaimer, I am not at all a regular user. So this, where did it go? Yeah, special thanks to Georg Lee and Jacques Zwa, my PhD students who are responsible for SplinePy. So if it doesn't work the way it should, I don't think I will be able to help, but I will do my best. Okay, so good luck. And